When we look at the physical layout of the modern world, from the concrete of a traffic grid to the copper of telecom cables, it appears as a wall of logistical noise. Finding the shortest path or the maximum capacity through these systems is difficult because we are distracted by the physical reality, the curves of the roads, the geography of the land, and the distances between points. But this logistical headache isn't new. In 1736, mathematicians were trying to solve these same puzzles before computers even existed. They found that to solve the problems of the physical world, they first had to learn how to completely ignore it. In the 18th century city of Königsberg, the Pregel River divided the land into 4 distinct areas, including 2 islands, all linked together by 7 bridges. A popular puzzle of the time asked if a person could walk through the city, crossing every single bridge exactly once, and return to their starting point. For years, people failed to find the route. Physical maps made the problem harder, as irregular shorelines and bridge lengths obscured the logic. Euler realized distance and shape were irrelevant. He simplified the map into points and lines, focusing only on how landmasses connected. Euler looked at the degree of each point, the number of bridges hitting each landmass. He deduced that if you enter a point and then leave it, you use 2 bridges. Therefore, every point besides the start and end must have an even number of connections. Since all 4 areas of Königsberg had an odd number of bridges, he proved the walk was logically impossible. This logic created the foundation of graph theory. We call the points vertices, representing entities like islands, computers, or people. The connections between them are edges, representing the pathways linking 2 distinct vertices together. In this model, physical properties, like edge length, curvature, or spatial position, are discarded. You can stretch the lines or jumble the layout into a new shape. As long as the connections remain, the mathematical model is identical. Graphs represent pure relationships, functioning as a mathematical tool that operates independently of physical space. To solve more complex problems, we have to add constraints. For instance, some systems only allow movement in one direction, like a one-way street or a sequence of computer processes. We model this using directed graphs, where edges become arcs, arrows that dictate the specific direction of flow through the network. Other systems have volume limits. A manufacturer shipping boxes needs to know which routes can handle the most weight. For this, we use weighted graphs, assigning numerical values to edges to represent capacities, costs, or travel time. By setting these capacities, we can run network flow algorithms to find the absolute maximum amount of material that can be pushed through a system. Translating these physical limits into math allows us to locate hidden bottlenecks instantly without ever needing to inspect the real-world infrastructure. Because this system ignores physical traits, it is universal. Vastly different systems in the real world often share the exact same mathematical structure. This circuit board is a physical network of copper traces and solder points. Using graph theory, we can model these connections to optimize how power moves through the hardware. That same mathematical model can represent a social network of human friendships, or track the path of a disease spreading through a population. We see it in history, too. These vintage mainframes use the same logic of vertices and edges to route data through early communication channels. Graph theory proves that an 18th century bridge, a modern circuit board, and your own social circle are all built on the same mathematical skeleton. Our world is defined by hyperconnectivity, where global supply chains and server farms operate 24 hours a day. Despite the massive physical scale of these networks, they are entirely governed by the simple relationship between vertices and edges. By filtering out the physical noise of geography, graph theory creates the mathematical framework we use to optimize and navigate the systems of the modern world.